Algebra 2, Chapter 13.2, exercises 17 through 22. This section of the book has to do with exponential growth functions, and I'm going to do, as usual, half of these problems in this 6-problem set. Usually I do only the odd number problems. I'm going to have a different order today owing to my wish for more variety. So I'm going to start with problem 18. And in this, I'm going to read the instructions first. Write the exponential function that will produce the given graph using the specified value of b. Verify that the second reference point is on the graph of the function, then state the domain and range of the function in set notation. So I'm going to go first to problem 18, and here we have a graph to the right. And what happens is it's not really clear in the instructions, but I'll explain how these reference points work. What we're going to have for b equals 2, what that means is our parent function for b equals 2 is going to be f of x equals 2 to the power of x. And what our reference points are going to be is if we have x, f of x, and we have an input value of 1, and then we're going to have an input value of 0 and an input value of 1. So in f of x equals 2 to the x, if we have an input value of 0, we're going to get 2 to the 0 power, or 1. And if we have our second reference, x value of 1, 2 to the first power is 2. So these are going to be our two reference points, and those are the ones we're going to have here. So this first reference point is going to be altered to become this one right here, which is -1 comma, let's see if I can read it, 5.2. So let's go ahead and see what we have here. Now, basically for a function, we have by the way, we have a horizontal asymptote at y equals 3. So what this is going to tell us for this function, and I'm going to write this as h of x. So we're going to have h of x equals a, which we don't know yet, times b, and we're given a b of 2. I'm going to go put this in parentheses here. 2 to the power of, we're going to have x, and we're going to have x minus h. Well, in this case, what happens is we have our first reference point here is h is going to be equal to -1. And so when we have x minus h, which is x minus -1, that's going to end up being x plus 1. So here we have x plus 1 up here. And then our k value, k is 3. Our k equals 3. So we're going to have plus 3 on the outside. Now we're going to use our first reference point here, which is -1 comma 5.2, and from taking this point here and putting it into this function here, we're going to have, I'm going to just write below, h of x is equal to a, and h of x is replaced by 5.2. So 5.2 equals a times 2 to the power of, and we have -1 for x plus 1, and then on the outside plus 3. Now 2 to the -1 plus 1 is going to be 2 to the 0 power, or 1. So we're going to be left here with is 5.2 is equal to a plus 3. And solving for a, if we subtract 3 from both sides of this equation, we have a is equal to 2.2. So therefore we can rewrite h of x with 2.2 for a. So here below I write h of x is equal to 2.2. Then we're going to have times 2 to the power of x plus 1, and then on the outside plus 3. Now in our instructions originally it says verify the second reference point is on the graph of the function. Well, we're going to do that by looking at our graphing calculator, and prior to starting this video lesson, here in y1 I've entered that function, and so we press graph and we should be able to see that we have the point -1, 5.2, and our second reference point is going to be 0, 7.4. So let's see if that's the case. Looks like it could be 7.4. Let's go for sure and look at our table view. We look at our table view, we have right here, we have -1, 5.2, and right below it we have 0, 7.4. So that's going to be a verification that we have the right answer. So this will be our answer here for function for number 18. And now says domain and range. So our domain, and we are asked to find the domain in set notation. Well, the domain for this exponential function, as in all exponential functions, is going to be x, such that x, we will say, is an element of all real numbers. And alternatively, in set notation, you could have written x is greater than -infinity but less than infinity inside this. That's an alternative way of doing that. And then our range, now our range is going to be, we are opening up here with this, with the graph of this function, so it's going to be y, we'll say y, such that y is greater than what k is, and k is going to be 3. So there we have our domain and range, and that's going to be number 18. The next one we're going to look at is number 19, and I chose this one for variety in that this is a graph, a function that is opening downward. So let's look at this again. I invite the viewer, as always, to pause the video and try to work ahead if you can. So we're given a parent function here of f of x equals 10 to the power of x. And that means that our original reference points that have been transformed here are going to be 0, 1. So we plug in 0, we get 1, and 1, 10 to the first power, 10. And we have a k value here. We can see a horizontal asymptote at y equals 4. So we're going to have k is equal to 4. And then we are to the left of the y-axis by 2 units. So our x-coordinate there is -2. So in this case, h is going to be equal to -2. And so writing out this function as far as we can take it, I'm going to write here the form h of x equals a times 10 to the power of, I'll put x minus h plus k. And in this particular instance, we're going to have h of x equals a, and we're going to have times 10 to the power of x, and since h is negative 2, that's going to be x minus negative 2 or x plus 2, and then outside k is equal to 4, so we have plus 4. And now our first reference point we're going to take is right here, this negative 2 comma 3.7. And so using this point of negative 2 comma 3.7, we get 3.7 is equal to a times 10 to the power of negative 2 for x plus 2, and then we have plus 4 on the outside. And so bringing down our equation, we have 3.7 equals, and 10 to the power of negative 2 plus 2, that's going to be 10 to the power of 0 or 1. So what we have is 3.7 equals a plus 4. And solving for a, we can subtract 4 from both sides of the equation. We have a is equal to negative 0.3 or 0.3. And that means we can fully write h of x as h of x equals negative 0.3 times 10 to the power of x plus 2, and then on the outside we have plus 4. So that should be our function, and we're going to go to our calculator to test that function. And what I've done, I'm going to turn off this function here and go down to y2, activate that function there, and I'm going to change this y4 to y equals 4 to see if this looks right, and we're going to graph and see what we have here. And so we hope we should have the points that we had originally here. And the reference, let's see, what is the second reference point we had here? It's going to be negative 1 comma 1. We have negative 2 comma 3.7 and negative 1 comma 1. Let's check that out. So negative 1 comma 1, that looks right. And let's go ahead and take the table view and see if it is right. Yes, down here at x equals negative 2, we have 3.7, and at x equals negative 1, we have y equals 1. So that checks out. Okay, so this is going to be a good function for us here. And our domain and range, or our domain is going to be set notation x such that x is an element of all real numbers, and then range. Now in this case we have a exponential function that's opening downward, so what we're going to have is this y such that y is y greater than k. No, in this case y is less than k or 4. So that's going to be our domain and range. Okay, now, next, and that's going to be the last problem we go to in this exercise set. Beginning with problem 21, we segue into finding functions that correspond with given situations, and then graph the function on a calculator and use the graph to make a prediction. So I'm going to skip 21 and go to 22 and explain about what the basic anatomy of an exponential function. The basic anatomy of an exponential function is this. There are different versions of this. I'm going to have A, as in capital A, for amount, equals P, and P, as in principal, our starting amount, times base to the power of our independent variable, which I'm going to call T. And so A is going to be our dependent variable, or a final amount, or resultant amount. This P stands for principal. And principal, another way to say this is initial value. Say initial value. Or you can call this the y-intercept if you want to. And B is going to be our base. And then T is our independent variable, and T is often used here to represent time. So I'll just write here time, because that tends to be probably most common use of independent variables in an exponential function in a real-world situation. But their base, B, is equal to 1 plus R, and R is our rate. Now in this case, our rate we see here is 8% per year. So R equals 8%. Now are we going to use 8% in terms of an equation? No, we're not, because 8% is going to be 0.08. So we're going to now write this equation. I'm going to write it over to the left here. I'm just going to write A equals P. In the place of B, I'm going to put 1 plus R to the power of A equals P times 1 plus R, and that's going to be to the power of T. And now filling in what we have here, we have principal, or the starting amount, is $1,000. So in the place of P I put 1,000, and then we have 1 times 1 plus 0.08 to the power of T. And then we have our finishing amount, which is $2,000. So in place of amount we put $2,000. And just simplifying the base, we have 2,000 equals 1,000 times 1.08 to the power of T. So now we're being asked how many years. How are we going to solve for T? Well, there are different ways to do that, but what I recommend at this stage of the course is to solve by graphing. And so for that, we enter both sides of this equation separately. So in our calculator we're going to put y1 equals 1,000 times 1.08 to the power of x. That's going to be in our calculator. and y2 is equal to 2,000. So let's go to the calculator, and I have not entered these previously, so I'm going to clear these out and get rid of this horizontal asymptote. Okay, back here at y2 we have 1,000 times 1.08 to the power of x, and then for y4 I'm going to put 2,000. And if we graph this, do we see anything? No, we don't. Our window is way out of adjustment for what we need. So what we're going to do is, for x value, we're going to go from 0 to, I don't know, 15, we'll say, as in 15 years, and x scale is 1. Y minimum, we can leave it at -10 or 0. And then we need to go up to $2,000. So I'm going to go ahead and put more than that, maybe 2,500, because I know that will get us. And our Y scale I'm going to put at 100 units. And then graphing, this is what we have. So we have the red curve going up from our y-intercept of 1,000 intersects. Now we can go ahead and we can trace and kind of go to the right here, close to, if we get to 2,000, I see this coming to, well, here's 1995. That's as close as we get by tracing. And we can see that we're at x equals almost 9. To get a more exact value, we can use the keystroke sequence second, trace, 5, enter, 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 and we get x equals 9.006. So x equals 9.006. So how many years? So that would be almost exactly 9 years. Now, it's beyond the scope of this lesson today, but an exponential equation such as this one can be solved using a logarithm solution, but we're going to leave that lesson for another day. I hope this has been helpful to you. Good luck, and thanks for viewing.